Okay. So it's nice to teach a graduate class because even if it's the day before Thanksgiving, lots of people will show up because nobody is expecting you at home. There are no parents to visit, nothing. So anyway, happy Thanksgiving. Hopefully, you will continue to have a great weekend. Um, One thing I should mention, I guess the reviewing part is going to be completed today. And we were generally quite, both I and Karthik were quite pleased with the level of seriousness that you seem to have given to it. I mean, we didn't yet we didn't go into every single thing, but it seems as if people have read the papers carefully, and in particular, people have also read each other's reviews and discussed. I think at least in one case, we had 16 comments, which is pretty impressive. Okay. In most cases, there are 2 comments, maybe 3, maybe 4, actually. 4 is pretty reasonable number. That means there are 2 reviewers. Each of the reviewers made a comment, and then they made one more comment, but there were, in some cases, there were like 16, and some other case, there was a 10, and so on. So that's kind of very nice. I think actually I don't quite know, obviously I can't speak for you guys, but it looks from our side that it was a good experiment. It seems as if it's very hard to make people just read papers and write reviews when nobody is reading those reviews. Okay, so really what you did is you made each other your peer reviewers. And I can just tell you that I ran several conferences, including most recently ICAPS, where I get to see all the reviews, as a program chair. And I ran CCI in 2005, and I believe I'm supposed to run ICHCAI in 2016. These CCI and ICHCAI are very many different communities putting together, and sometimes the reviews aren't all that different from the kind of reviews you guys wrote. Okay, the point about peer reviewing is essentially people, you are at the same level as everybody else at the frontier of the current research. Okay, so it's not necessary that somebody is trying to find easy flaws in your paper. If it is a reasonable paper, there is no obvious flaws, and so I think it worked out well as an experiment, and so that's thanks for taking that seriously. Okay, before I start, are there any questions? Okay, so actually these couple of lectures are going to be, I think the topics are fascinating topics, and I think all topics in this course are fascinating, but these ones are also very nice, and they are like you can use them for all sorts of interesting applications, but most people use them. So for example, by the way, the LDA project that you're doing is essentially like playing with the MDP applet. You really are not being asked to do any theory or any coding. You're basically being just asked to use an LDA program that's available there. And so all of what we are doing here is the theory behind it. Okay, so the specific way the topic models are fit. Okay, those sorts of things, that's what we are going to learn here. But you are not actually using it, you are not implementing that yourself. Okay, so hopefully you are in between somebody who just uses the toolbox without knowing why the tool works, and somebody who can implement the toolbox and use it. You will be somewhere in between, by the end of these 4 lectures. Okay. So I said basically we talked about a unigram model, and we talked about single topic model. And then I also sort of quickly went from single topic model into LDA, but I'm going to restart again at the single topic model just to make sure that the ideas sort of take root. Basically, I think there are a bunch of things. For those of you who have not done any machine learning courses, for example, before, which probably are most of you, there's several things that come in, in this whole Bayes network and statistical models things. And they all fall in nice place. So for example, today you will see that things like unsupervised learning that you may have heard about, or dimensionality reduction that you may have heard about, they all just become special cases of things that we are doing here. Okay, so it's a very interesting way of looking at the learning, language learning. Okay, so going back to unigram model, we assumed that all documents are being populated with words drawn from the same distribution. Okay, so if there are V words, then there is a V-dimensional discrete distribution that essentially tells you the probability that each of those words are picked. Okay, and presumably I just am picking from using that distribution. I'm picking the words and putting it in the document. You want a next document? I'll do the same thing. Next document, I'll do the same thing. So while the documents will probably have different words, okay, but probabilistically they are the same. Do you understand what I'm saying? So for example, if you tossed a coin, you got heads, heads, tails, tails. I took the same coin and I tossed it. I got tails, heads, tails, heads. They look very different. Do you see what I'm saying? They look very different. They're not the exact same data that you got, but they're essentially the same. In fact, in this example, you got heads, heads, tails, tails. I may have gotten, tails, heads, heads, heads. So that means not even the numbers are the same. It's not just the order. Even the numbers are different. But that still is fine because the data is being generated by the same underlying probabilistic model. The probabilistic model basically says with probability 0.5 generate an H and probability 0.5 generate a W. By the way, coin toss, think of, for today's class, think of coin toss as a language model. Okay, it's a language model with how many words? 2 words. It's just 2 words, okay? And so you can write, so basically, in fact, one might actually say that all the binary files in the world can be generated by this model, right? Because it's just zeros and ones. Binary files are zeros and ones. So I'm just tossing coins and generating zeros and ones and putting together. Okay, actually keeping that analogy in mind is very useful because essentially I'll bring it up later on too. But essentially, so as I said in the context of this example, the 2 coin tosses. If he tosses coin 4 times and he got like a 4-word document which was HHTT. I tossed the coin 4 times. I too got a 4-word document. However, mine said THHH. These documents look different superficially. But my point is that probabilistically they are the same. They're both using the same kind of a coin. What's more interesting is this guy has a coin which comes heads 0.3 probability, tails 0.7 probability. He tosses his coin 4 times. He too will get a document which is in HTHH form. Sometimes his document would look like your document. What we are trying to do is if he keeps tossing his coin and generates large number of documents, you do the same thing with large number of documents, and I do the same with large number of documents. There would be macroscopic differences in the word distribution in the documents we are generating. Eventually, his and mine will have 50% heads, 50% tails. His would have approximately 30% heads and 70% tails. Do you see what I'm saying? Okay, this is actually particularly with respect to this question that I had last class as to, if you're generating statistical models, exactly how can you understand language? I'm not trying to understand the meaning of a single sentence. I'm trying to understand the makeup of the words falling into sentences. Falling into the document, not even sentence actually. And what's interesting is even at that very, word level, word distribution level, we can make all sorts of, useful conclusions about language. Okay, fine. So in the case of unigram model, essentially it's like, there is a single, single particular distribution with respect to which the documents are being generated. And now when you see the documents, you need to learn this distribution. And once you learn the distribution, you can generate your own documents. Do you see what I'm saying? So I look at this guy generating his documents. I see some of it and they say, oh, no, I don't need to see your documents anymore. I figured out you have a 0.3, 0.7 according to my model. Okay, so I'll just look this side and start generating my documents. They will look like yours, probabilistically speaking. Similarly, if I'm looking at yours, I'll learn maybe 0.5, 0.5, and then I can do the same thing. That's what is going on here. Okay, I mean, this may be obvious to some of you, but if you are thinking for the first time at this level of documents being made into words and bags of words, which is basically what we are doing, it's not at all obvious that to completely do, different documents actually, I mean, you can use the same distribution but can get quite different documents. So he and I were getting different documents, he and I were getting different documents, but the difference with him is bigger than the difference with him. Because in both our cases, it's the same generative model. So if I had enough examples, we would have been the same, essentially. With him, I'll never be the same. So that's the thing to keep in mind. So anyway, unigram would be basically learning one single distribution. I mean, so it's assuming the generative model like this. And whenever I have a generative model, if I show the data, you can compute the parameters of the model. And once I compute the parameters of the model, then I don't need the data. I can generate the data. The beauty of generative models is you can generate the entire data back again. Okay, keep this in mind when we talk about something called discriminative models, hopefully next week. Okay, in the case of discriminative models, you may be able to do predictions, but you may not actually be able to generate the data. Here, this is the way you generate the entire data. Okay, so that's the uniform model, and then we thought that was, and again, the way the parameters, in our case, what you need to learn is V. The distribution over the words, the word distribution. You could do it using essentially MLE, maximum likelihood estimate. You can do it with MLE plus some sort of a Laplacian smoothing. Or you could do it actually as a Bayesian learning, which I'll again get a chance to tell you, quite a bit today. Bayesian learning is an oxymoron. Okay, I mean, I hope you will remember this after this course. Okay, if you ever read a paper on Bayesian, oh, by the way, the paper that got the highest mark according to the reviews was the Bayesian reinforcement learning paper. Whoever read, the two people who read the Bayesian reinforcement learning paper were smitten by it, and they gave the highest marks. And so, in fact, we're going to share some of this information with you guys so that not only would you know about the two papers you read, the papers you read, first of all, I mean, I'm making a little digression. They were from just this ICHCA and IIII. So they are at the edge. They are right now being done. Okay. The fact that you understood some of it is good, right? And secondly, Bayesian reinforcement learning actually, I mean, so we would like to show you the ranking in terms of the average reviews. Okay, I think we'll send you the ranking, and then you can decide which papers you, other than the ones you read, you want to read. We'll also send you all the reviews, so just for your this thing. Okay. Anyway, so there is a Bayesian reinforcement learning or a Bayesian learning. There would never be a section called learning in such a paper. If there is one, then you should be worrisome. You should be worried because this guy must not know what Bayesian learning is, because there's no learning in Bayesian learning. You see what I'm saying? Typically, what we mean by learning is that we say, this is the hypothesis I'm going to go with. And what I tried to do in the last 4 weeks, if nothing else, is that Bayesians don't make up their mind. They just keep changing the probabilities around. They'll never say, this guy is my winner. Okay? So it's all inference in Bayesian learning. Okay? So you could do that too for the unigram model. I'm just not going to talk about it. I'll talk about basically Bayesian inference with respect to LDA, which is worth doing anyway, because that's the most complicated case. But you can do it here too. Okay, fine. Then we talked about the single topic model. which I want to repeat today a little bit more. So in the case of single topic model, essentially each document has a topic Z. So the assumption is you don't like the fact that all documents are being generated with the same word distribution. That's what you don't like, because that's just too simplifying. Okay, even if in fact the numbers, so basically all of us are generating it with either the 0.3, 0.7 or 0.5, 0.5 distribution. That's it. You would like to say that some documents are generated with different documents are generated with different distributions. That's what you want to say. But if you want to say that every document is generated with a unique distribution, then there is no learning to be done. Do you see what I'm saying? If every novel is different, then there is no point for taking AP Literature or Iowa City Writers class. There's nothing you can learn about how to write a new novel. There is, however, some commonality in the way novels are written. There are some topics. There are, some, structure. It's not as simplistic as the unigram model, but neither is it as complicated as everybody has their own distribution. So the way we bring that in is we'll say every document is about a specific topic. Topic is just a code word for saying, so if you have D documents, for generating each of these documents, you need a word distribution. The maximum number of word distributions you would need if you are trying to generate D documents would be D. Right? Okay. If you do that, then you may as well just say for each of the distributions, I have exactly one example, and you might as well learn it from that. Instead, I would say I have K I'm only going to learn K distributions for all these documents. K was equal to 1 when you had no topic for document. Assume when there is no topic, so in the previous case, actually I would say there was a topic. It's just that all documents are with respect to that universal topic. Now I'm saying each document is with respect to one of K different topics. And the K is just a stand-in for the number of distributions you're going to learn. So then I will just say, once I pick the topic, then with respect to that topic, I will have a distribution of words. Right? Now, just to put this in perspective, you have to realize, and it's very important to realize, that what we are saying by topic is the distribution over words. Okay, so I told you earlier that the kind of topics we'll talk about is, well, a topic could be, for novels, a topic could be science fiction, and our romance, our history. Now, if there are V documents, V words in the vocabulary, how many probabilities do you need to give to specify the science fiction category? Just one topic. Okay, it turns out it doesn't matter actually. So here's my question. I am trying to define this topic called science fiction. And my language only has V words. How do I define it according to this picture? I just have to give a distribution. Distribution over what? The words. How many words are there? V. Previously, I just gave you one V distribution for the unigram. Now I give one V distribution for each of the topics. That's it. Do you see what I'm saying? And those numbers, do they all have to, so for example, so here are two categories, okay? So the same words, so for whatever reason, these are the words in my vocabulary. Okay, here is a topic 1, and here is a topic 2. And you specify the topics by providing the distributions of the words given that topic. That's it. Okay, do you think that if you add all of these numbers and all of these numbers, the total should be 1? Of course not. Don't shrug your shoulders. No, it should not be. These numbers should be 1. These numbers should be 1. There is no connection between these. These are conditional probability tables. That's exactly what they are. This is PW given category equal to 1. This is PW given category equal to 2. If I give you a Bayesian network with bunch of conditional probability tables, do you look for some kind of adding up numbers in all the tables to get some patterns? No. The only thing is, there is somewhere there is a category variable which will tell you that with 0.7 probability you take category equal to 1 and 0.3 probability you take category equal to 2. You see what I'm saying? That's exactly what was going on here. So this variable is the category variable, and it would have a distribution, prior distribution. What's the prior probability that the category would be in a science fiction versus history versus romance? And using that prior probability, you pick a topic. Once you pick a topic, then you just look into the distribution corresponding to that topic and generate the document. Do you see what I'm saying? In the unigram model, there was only one distribution to begin with, and you just use that to generate the documents. Here you had to make two decisions. One, what is the topic of the document, and after that you just, okay. Now, given that, if you want to quote unquote learn this model from the data, that means if I just showed you some amount of documents, previously in the unigram case, all you needed to learn is the word distribution, one single word distribution table. That's it. Here what you need to learn is both the word distribution per category and the prior distribution over the categories. You see what I'm saying? Because if I have basically if I have a 2-word documents, so I have a category variable and it causes word 1, it causes word 2. I say cause, but really, this is Bayesian causing, okay? And then, and of course, since there can be any number of words, I put this in a little square, one word in a square, and that becomes the plate model. Okay. Now, of course, for each document, you have one category. You pick a category again. So there is a little square for the W, and there is a bigger square for W and category. Bigger rectangle. That rectangle is the document rectangle. This is within the document how many. So this is, you normally put the number of times you repeat this structure. So D, so you repeat this rectangle D times. And then the nested word is repeated, whatever N, which is number of words per document. So if you do the whole thing, it looks like a really ugly, huge network, but you just wrote it as a small one here. But when you want to learn, you need to learn the prior for this, and you need to learn the conditional of words given the category. Those are the two things you need to learn given the documents. Yeah, there was a question.
Yeah, can the probability be 0?
Which one?
That scientific in any category.
No, which probability? These?
Yeah.
Of course, I made it 0. Just now I made it 0.
But there is some probability like 0.0001 or.
No. Again, theoretically, you can make probability 0. Nobody stops you. But there are practical implications. Okay, in fact, one of the interesting things is, if you remember, by the end of last class, I was singing praises of sparse distributions. Distributions which make many probabilities 0. There is an advantage for that. Okay, if you make probabilities 0, now of course that distribution is not over words, but actually was over topics. But if you have sparsity, it has some advantages. But when it becomes 0, it also is the case that you have made up your mind upfront. Do you see what I'm saying? And so no amount of knowledge will ever unchange it, because 0 is forever. Okay, theoretically there is nothing wrong, but in practice that means you are really damn sure that that word will never occur again. So the movement, so this is great, right? Because if the movement, if you see the word soul, it cannot be from this topic. You see what I'm saying? Lovely. So lack of, so basically the very presence of the word tells you it cannot be from this topic. Okay, I mean, but you better be very sure, right, that this is actually the case. Okay. Any other questions? Yes.
I guess, is there any way to sort of solve for topic similarity based on, like, if you have multiple topics with different priors that somehow generate things very similar to another singular topic that's not included?
So the question, maybe what you're asking is there any way, if there are multiple topics, can I talk about the similarity between this topic and this topic?
No, like if you have, say, 3 topics,
yeah,
and some mixture of the first 2 generates something approximating like the mix you would get from the third.
So we haven't yet, okay, so for now we haven't yet started combining topics, okay? But you can ask the following question. If I give you, first of all, I just said topics are distribution over words. Okay, but you do know that some topics are closer to others than other topics. So for example, in the grand scheme of things, okay, a topic mathematics maybe is close enough to the topic physics, maybe is quite far away from the topic religion. Do you understand what I'm saying? How do you, that's a reasonable question. Is mathematics as a topic closer to religion or to science? Okay, but there is an elephant in this room, by the way. When I say mathematics as a topic, so here I just said category equal to 1, category equal to 2. This is topic 1, this is topic 2. Topics don't come with their names. No amount of learning says the first topic happens to be mathematics. Okay, the thing that you have to realize is when you learn topics, you will learn these distributions. Typically what you would do is you will put, just as what we did here, you will put the words in the order of their probability. For visualization, the computers don't care. You give them a distribution, they'll use it. If you want to understand your machine is working, but exactly what is it doing? It seems to be saying topic 1, topic 2, it seems to be good. Exactly what is topic 1? Exactly what is topic 2? Then you can look at that distribution, which is a v-dimensional distribution, which is a large distribution. Very painful to look at it, where if you have 10,000 words, 10,000 numbers all adding up to 1, you can't tell what's going on for a while. So what you do, you just sort them in the order of their probability. And look at just the top 10 words, let's say. That should typically give you a feel, a qualitative feel about the difference in the distributions. Okay, for example, the distribution corresponding to a topic that you want to call religion probably has a pretty high probability to words like God and prayer, etc. Okay, whereas a distribution that you are calling science would probably not have that higher probabilities for those words. So to understand, the first thing to understand is topics are themselves living on the word simplex. It's a beautiful way of saying something simple, right? I mean, if you're not into math, okay? Basically, a word simplex is you have V words. So you have a V-dimensional space. Okay? The V-dimensional simplex is any set of points in that space such that their coordinates are between 0 and 1 and they add up to 1. Right? In 3-dimensional cases, the simplex looks like a nice triangle, which is why people put pictures of triangles when they talk about simplexes. Really, there is no picture of a 4-dimensional simplex that I know of. Okay, but a simplex essentially is, the subspace in a space which has the same dimensionality, but the coordinates of the points living on that particular subspace add up to 1. Now, as far as you're concerned, this means these are both v-dimensional vectors. They're both v-dimensional vectors. So topics are vectors in the word space. That's somewhat more general than what they really are. Topics are vectors in the word simplex, because word space would mean these numbers can add up to more than one. Right? Okay. Now, when you want to ask which topics are closer to which, you're asking a question: which two vectors on a simplex are closer to each other? Which two vectors on a simplex are closer to each other? So any reasonable metric for talking about the similarity of two vectors would work. In particular, for probability distributions, the distance metric that people like is KL divergence, which takes two distributions of the same size and tells you how far apart they are. And it will be 0 when they're the same. Okay? And basically, so it's a way of just, giving distance between two vectors which happen to be probability distributions. But this is a useful thing to, even though I don't even know whether this was anywhere near the question you were trying to ask me, but this is a question I want to answer, which is basically to realize topics aren't created in some higher level world. Topics are just probability distributions over words. So they live in the word space. Right? Now, in a single topic case, where do documents live? Each document is a single topic. Each document is a single topic. Right? So notice that in a single topic scenario, for each topic, you've computed these distributions already. Right? Okay? I'm trying to give you a new document. How much information do I need to give you about that new document so that you know everything about that document, statistically speaking? What? No, the distributions are already there. So I know that there are only two topics, and this is the distribution for the first topic, this is the distribution for the second topic. Here is a document. I have it right with me. What do you want to know about it? Which topic?
The distribution.
Which topic? No, not the distribution, just which topic. I want you to get this really, really into your head. Okay? The information I need to give you about this hidden document I have in my hand. Previously, I had to show you the document, and then you will probably do all sorts of things. As far as this level of analysis of documents are concerned, once I figured out the topic word distribution, everything that you want to know about this document is completely specified by the topic of this document. Completely. Now you might say, that's not reasonable. I know there are different words in different orders, but that's all statistically the same. Remember, when he got HHTT and I got HTTTT, HTTT, so 3 T's and 1 H, and he got 2 H's and 2 T's. They are the same document as far as we are concerned, because they are essentially coming from the same coin. This is the reductionism that you did. Okay, this is the reductionism that you did. So you can play your game saying, no, this document is different from that document, but your program is not going to differentiate between them. For your program, they're exactly the same. It's the topic that matters. So what did you do just now? You took a document which required, if a document has n words drawn from V vocabulary, it typically, according to the first slide before unigram model, I needed to tell you each of the words in each of the positions. I needed to tell you all n words in the exact order they are present in the document. According to this model, all I need to tell you is This is a science fiction document, so write it yourself. There's nothing much different about one science fiction with another, because supposedly, according to our model, they're just sampling words from these distributions. It's important to know this so that you won't be surprised. I mean, you're making this, huge simplifications. In the unigram case, I have a document in front of me. How much information do you want to know about it? What do you want to know about it? I have a document right in front of me. I'm holding it. Basically, assume the distribution is always given, right? That was the same case. So you don't even need to know. Oh, you have a document, I'll make a document. That's what unigram is saying. Okay? And the single topic one is saying, you have a document, tell me the topic, I'll make the document. You can think of this. You can think of this as previously, documents were vectors in a v-dimensional space. Now I said all that you need to know about your document has been reduced to this magic number called the topic number. Dimensional array reduction. Have you ever seen dimensional array reduction in your life? What? Well, yeah, nobody knows what CGPA is other than you and I, but GPA. Okay? I mean, you guys think I'm so different. My friend has, messed up the first exam, did the second exam well, again failed in the third exam, and all this major story you will tell, right? And then I, on the other hand, did badly in the first year, better in the last year. And my other friend took easy basket weaving courses and got a very high grade. I'm taking these crazy courses and I'm, getting killed. Okay, you can tell large numbers of stories. What happens if you tell this entire story? I need to make sense of this story. So I want to reduce the dimensionality. I'll say I'll give you one number. Thou shalt have GPA. You could get the same GPA in 8 different ways. In fact, 18,000 different ways. Do you see what I'm saying? I reduced you all to your number. I mean, as a student. Now, every once in a while, people will argue that, no, this kind of dimensional reduction makes no sense. You cannot take the variation of people and put it into one single number. And so I know some of you know my story that, UC Santa Cruz is this nice hippie style beachfront university, outside San Francisco. And they believe that, people cannot be reduced to a single number. So they did the right thing, which is they will say at the end of each course, the faculty member is supposed to write a single paragraph. Now, one might argue, what's the number versus paragraph? But at least this is, each course, I'll give you a paragraph, writing about you, about your performance in the course. And then your transcript would just be a concatenation of all these paragraphs. And then they found that Santa Cruz students were mostly hanging around in the beaches, not getting any jobs. Why? Because nobody wants to take the time to read the paragraphs you carefully wrote. Do you understand this? This is the way the world works. You may decide, I don't want to reduce the dimensions. But if your employer wants a single number, you better give them a single number. If not, they will add up all the words divided by the total number of words in the English and say, that's your GPA, multiplied by 4. You see what I'm saying? So you may be saying, how can you reduce the document to a single topic, but you are reducing your life to a single number GPA? And there's a good reason. And there are, of course, bad and good ways of reducing this. But this whole idea is dimensionality reduction. This one, eats the cake a little too much, right? Because it just went from, v-dimensional vector to one-dimensional vector. Do you see what I'm saying? Okay? This is the important thing. You will hear the word dimensional reduction being talked about a lot. But essentially, that's, picking a topic is reducing the dimensions. Okay? Now, just a little further, if I say it's not a single topic, as I said last time already, I mean, I want to consider a mixture of topics. Fine. So then each document would be a distribution over the topics. There are V number of words. How many topics are there? Hopefully way, way less than V. There are like only K number of topics, and there are V number of words. Do you see what I'm saying? In which case documents are now people, they are vectors that live in the topic space. Topics are vectors which live in the word space. So everything, there's turtle under turtle under turtle. Okay? But now documents can be thought of as vectors of K dimensions. They're K-dimensional vectors. You just need to tell what is the mixture of topics you are picking for your document. Once you pick me the mixture, I will generate the document. You have to give me K numbers to specify the document in the mixture case. In the single topic case, you just have to tell me the one topic for which it's non-zero. In the case of Unigram, you don't need to tell me anything. I'll just generate documents. You have documents, I'll make documents. Okay? Right? So one other thing to understand, again, that should be obvious, is really what is happening. You can think of what is happening in the single topic case either as basically documents are not only living on the simplex, but they live at the corners of the simplex. Right? Basically, they can only be on one of the axes, because everybody else has to be zero. Whereas when you go to LDA, you allow documents to live in the middle of the simplex too.
So when you're specifying the K numbers for multiple topics, so all these numbers added to one, should that be a probability distribution?
Yes, that's the mixture, yes, exactly. So each document will now be a probability distribution over K topics. Right? Okay? Okay, we'll get to that again in a minute, but that's the point. Okay, so let's see, what else do I want to say here? Now, of course, I do want you to think of this as the connection to Candy's aspect. I already said documents can be thought of as coin tosses, outcomes of coin tosses, and you better understand it. That's the level at which you are looking at the documents, and that's also the level at which Google looks at the documents. They essentially looks at the bags of words, bags of outcomes. Okay. So in the case of Candice, remember there was a hypothesis. Actually, in fact, no. Connection to Candice. So you are essentially guessing bag types, except I think this is not a good example. Let me not go into this right now, because it may well be that each bag type has percentages after, no, it's true, it's fine. No, each bag type is a topic on the candies. Each bag type is a topic on the candies. Okay? And there were 5 types of bags. So there were 5 types of topics. And you're writing your essays, your novels in a much sweeter format in terms of lemon cherry candies. Right? That's the connection. It's the same thing. Okay? Okay, let me get you to one more thing. So one interesting thing I want you to understand is that we just saw dimensionality reduction come into the discussion, because topics are reducing the dimensions of the underlying document. Right? Okay, so the second question, of course, that I want to discuss with the single topic, because everything we discuss in the single topic would be needed also for the LDA. Everything we discussed for unigram model was needed for this. And then everything discussed here will still be needed for LDA, because that's just a one more step generalization. Okay, so the question is exactly, yes, you have this model. So you have a model like this. I have a category, and let's say I have only 3-word documents. So for each document, I have 3 words, W1, W2, W3, and then this is repeated once for each document with the same exact distributions. Right? That's the thing. Right? Now, I gave you this topology of the network. And then I gave you training data, which is basically the documents. So the question, of course, is how do I phrase this learning problem? Previously, the learning problem was essentially the structure was each word was its own vertex, and there was no parent node for it. Now there is a topic node, which is a parent node for the words. So now when I give the documents to you, when I give you the documents, you certainly have the words, because in each document there are words, and I'm showing you those words. Is that if I just show you the words in the document, am I giving you the complete data case or the incomplete data case? Incomplete data case. If I were to give you complete data, that would be just supervised learning. One more word that you may have heard in other places. Okay. The beauty of statistical learning is that all these things which are studied as separate topics can just be mixed and matched within the same model. Okay, so it's the same structure. This is the same story you are sticking to. Once you pick the generative model, okay, I can give you training data either in format 1, where I will say, okay, here is a history document, and these are the words. Here is a science document, these are the words. Here is another history document, these are the words. Here is another science document, these are the words. Now, I just want you to basically learn the model. Those of you who have heard of naive-Bayes classifier, you're looking at it. Because when I gave you the labels, you can think of the history document, that name history as the topic, that's the label for the document. You can think of this as the document features, this as the class of the document. So topic is the class of the document. If I give you training data such that I give you the class as well as the document, then I'm essentially doing supervised learning. That's just naive-Bayes classification. Did people see this? How many of you have heard of naive-Bayes classifiers before? I hope you see that that's just what it is. Naive-Bayes classifier is essentially a single topic model on words where you give the topic for each of the documents. Now, to the extent I can think of bags of candies as documents and outcomes of passes as documents, I can think of pretty much any classification learning problem as a document. The features are the words and the class name is the topic. That's it. So now, since this is a Bayes network and I give you complete data, you jump up and down because learning is so easy. At least the MLE learning is so easy. Just to remind you, here is basically a repetition of how you train a naive-Bayes classifier, which should not be needed for you because you already know why. You already know why complete data learning is easy. Okay, the thing that I want you to remember, by the way, everybody knows that naive-Bayes classifier learning is easy because it's just all the parameters are just ratios, right? But hopefully you know definitely after this class that what makes it easy is not because naive-Bayes classifier is just one level, rather two levels. Okay, the class causes attributes. That's not the reason why it is easy. It's easy because it has complete training data. Complete training data means you need to provide the class label also. Do you see what I'm saying? So this could be a problem if you are hoping to figure out what the topics are by just looking at the documents. Right? So that means you have training data which only has the words, no topic names at all. In that case, it would be an incomplete data problem. For machine learning from another direction, it's it's now unsupervised learning. What do I do about it? But from a generative model based statistical learning perspective, it's the same thing. It's just now I have incomplete data and I don't give up. My life becomes slightly harder. How does it become slightly harder? I now have to do EM. If I want to do MLE, I need to do EM. That's it. Okay? So the thing to understand is that you can have incomplete data where you systematically ignore giving one particular attribute. It's a hidden attribute. In this particular case, topic is a hidden attribute. I systematically ignore giving the topic because I don't know what the topic is. And you will still find K topics. If you ask me to find K topics, I'll find you K topics. Because there would be K different distributions over words. Do you see what I'm saying? That's what you guys, there were questions in the, I asked you to redo the second step of EM problem. In the second step of EM problem, you didn't know what the bag names are. Right? The data came with just the candies, no bag names. That is basically showing documents without their topics. And you still figure out what the topics are. You still figure out what the bag bag distribution over candies are. You see what I'm saying? If it works there, it will work here. The thing is, there's no magic. You can systematically ignore giving topics. Now, a question is, by the way, so naive Bayes, you know this, right? Essentially that you can do the counts. MLE based thing, you will do the counts. And one other thing you can do is you can do an adjustment to the counts to avoid zeros, avoid overfitting. And that we basically can say that the usual thing that you would do is you would say that essentially in this case, now I'm adding a 1 on the top and a V in the bottom. All that we are saying is that we have looked at V words before you looked at the first word of this document. And those V words came using basically some uniform distribution over the words. And I told you earlier that what we are doing here without much of a semantics, just to avoid zeros, winds up being what will happen if you did Bayesian learning. Once again, Bayesian learning has no learning, that's fine, but essentially what Bayesian would predict would be, equivalent to essentially adding to the counts, virtual counts. By doing this, in some sense, you got the Bayesian. Okay, so that's regarding the knowing the topics. If you don't know the topics, of course, you essentially do EM. To do EM, what do? You guess a label. With respect to the label, so you guess the parameters, and with respect to the parameters, you compute the likelihood of the data, and then with respect to that, you recompute the parameters and so on. That's what you did in EM. The mind-blowing thing that you want to get, basically wrap your mind about is all I'm telling you is there are these documents, find K topics, just K topics, such that each document is from one of these topics. And you need to figure out essentially K distributions like this. K distributions like this. When you did that, you figured out the K topics. I did not tell you anything more other than just find K topics. That looks almost impossible to do from the, basically from the looks of it, right? But essentially, if you view it as EM, that's what EM does for a living, right? It computes, essentially, it has this likelihood estimate which involves summation. right? Because whenever you see an incomplete data, the thing to remember is that suppose I found W1, W2, W3 as the document, it could have been caused by category being topic 1 or topic 2. Do you see what I'm saying? There are people who are basically seen as science fiction writers who have written romances in science fiction category. Okay, given the book, you probably would tell, oh no, this is some kind of a, like some kind of a Harlequin romance writer wrote this. You could, but there is a small probability that a science fiction writer can write it. Okay, so when you see just this, you marginalized the category. This is what somebody, I think you asked this question and I was telling you, this is what you do in EM. You marginalize the category. So to compute the probability of this given the model, you need to consider topic being 1 and this, and topic being 0 and this. Add those probabilities up. That is the probability of seeing word 1, word 2, word 3. It is this summation in the likelihood that makes your life unhappy in terms of optimizing this expression. That's why you needed the EM. Because log of sums doesn't behave well. Log of products, very easy. Log of sums, not very good. Okay, and the thing to remember in this case is what exactly is EM optimizing? When you found, so here is a very interesting question. How many topics am I supposed to find? Yeah. Well, it's better than always assuming there are 0 topics. I mean, it's better than always assuming there's 1 topic. Do you understand what I'm saying? Okay, so here is a very interesting picture. Here's a very interesting thing that you can do, and this you can do also. By the way, whatever we are doing here should remind people of k-means algorithm if you have done k-means algorithm. Where is k in the k-means coming from? You just made it up, right? Right? And in fact, if you think in terms of the optimization of what k-means is doing, which is intra-cluster similarity, it will be the highest if k equal to n, which is each point is a cluster by itself, which means for us the right number of topics is equal to the number of documents. Each document is its own topic. You see what I'm saying? So here is an interesting thing. Suppose I am given a bunch of documents, 1,000 documents. I could learn a network like this with topic being 1. That means there's only 1 topic. If I have exactly 1 topic, that's like unigram model. 2 topics, 3 topics, 4 topics, 15 topics, all the way up to D topics, where D is the number of documents. You see what I'm saying? And how do I compare these models then? What's the common currency between 2 models? Likelihood. You learned a model. Tell me with respect to your model, what's the likelihood that you saw the documents that I just gave you? You see what I'm saying? I mean, one way in which you can think about this is, we talked about models in this class all along, right? And models and planning can be only done when there's models and so on and so forth. And the interesting thing is that if you don't have a model of how the world works, you are perpetually surprised. Everything is a surprise. So I dropped the pen, it fell down. I'm very surprised because I didn't expect that. Because I have no model of this world. Do you see what I'm saying? If you have a good model of the world, you have no surprise. You're always bored to death. So to the extent you believe in God, your God is bored to death. Because they know exactly what's going to happen. Everything is exactly as specified. They have a complete model, supposedly. Most religions believe this. Okay? So the interesting question is, I'm going to give you the models that generated this document. The models that have generated these documents could be based on the stories I tell. I'll tell a unigram story. That means there's a 1 topic story. in which case I'll get a one topic model. I'll tell a two topic story, I'll get a two topic model. I'll tell a three topic story, you'll get a three topic model. Which model is better? The model that is least surprised in the end by the data that I have provided. You see what I'm saying? One thing you could do is if you want to be scrupulous, then suppose you have 1 million documents over which you are learning these models. You keep 1,000 of these in a vault somewhere. Don't look at them during the training, right? Okay, and then you learn the models, each of these models, with respect to these 1 million, 900,000, 999, blah blah blah. Okay, and then you would get the model. With respect to that, you compute the likelihood of these 1,000 held out documents. Okay, and plot the log likelihood. Okay, what do you think will happen? It would be the highest when D equal to D. Sort of, probably. It will be somewhat low here. But the real question you would be interested in seeing, if you have the time, is maybe it's sort of, maybe it's kind of low like this, then goes fast, and then sort of becomes like this, where this is the K topics. So then I'm looking for the knees in this curve. Those of you who did k-means, that's the way k-means, the K for k-means has to be found by trying out various Ks and seeing where the mean is. Okay. Most likely, most people don't even do this. They'll just say, let's fit 7 topics. Let's fit 20 topics. And then just see what happens. Now, what is interesting is, this is going to be monotonic. You fit 7 topics to the data. The likelihood would be higher than if you only fit 6 topics to the data. It may not be particularly high, but it can be lower if you did your work right. Because the 7 topic one could basically just, essentially say there are no documents with the 7th topic has probability 0, and it will become 6 topic 1. You see what I'm saying? Okay, now having looked at this, if you're somehow still very unhappy that K has to be picked, you really shouldn't be, because previously you did not even have a chance to give a K. But if you are unhappy, then read all about Bayesian nonparametrics, where in essence you don't need to pick the K up front. Okay, I won't go into that at all. It's like even more frontier right now. Okay. So basically what you're doing is you're fitting topics. When you got the right topics, that when EM actually gets to a good global maxima, which of course there is a problem. Again, this particular curve is theoretically what you should find. But since this is all incomplete data and you are running EM, you may well get stuck in local optima. And so even though I said the log likelihood for a 7 topic case cannot be less than that for a 6 topic case, if I got stuck in a bad local optima for 7 topics and a better local optima for the 6 topics, then I can have wiggly structure. Okay? So that's what's going on behind the single topics. And once you wrapped your mind around single topics, by the way, so I don't know if you can see this thing. Maybe I'll try to remove this. If I don't give you a topic, that's just unsupervised learning. So the light bulb is unsupervised versus supervised is nothing but complete data versus incomplete data. Now what am I hiding? So machine learning makes huge difference between unsupervised versus supervised. right? We are just saying that's just the distinction between having complete versus incomplete data. But I do still have a choice I am making without looking at the data. The choice is my generative model, the story I want to tell. You can call that a bias. If you are looking for K topics, you will find K topics. You see what I'm saying? In a normal unsupervised learning framework, you don't actually get to decide, among all the single topic models of this type, which one will fit best. You don't get to decide that. I'm not even telling you anything about how this data is actually organized. Here you are essentially, for example, saying the words are all independent and that they are conditionally independent. They're all conditionally independent given the category. Okay, if these are like 3 words and 1 category variable, this is not the only network you can draw on this. Right? This is not the only network you can draw on this. You can draw lots and lots of different networks. So what I pushed under the mat carefully is if you make up your generative model, you already decided the topology of the network. Remember, we did talk about in Bayesian based network learning, we talked about not just complete versus incomplete data, but we also talked about whether the topology is given or not. The really hard problem would be to say, I don't even know the topology of the network. And that's a pretty darn hard problem. Because when I say I don't know the topology of the network, I don't even know how many hidden variables are there, how many layers of the hidden variables are there, and how they are connected. The huge assumption I'm making here is this is the story. I'm going to stick to it. The topics cause words. And you can think of this, from a statistical learning point of view, this is the generative model. From machine learning point of view, general machine learning point of view, this is a bias. You're biased to find models of this type. Among the models of this type, which is the best fit model for the data? There may be completely different models that are even better fit. Right? In fact, the next thing we're going to talk about as usual, in like the next 5 minutes, is, okay, by the way, so this I'll come back to next class. But it's worth looking at this, by the way, that even though I was talking about learning, basically we had this model. I showed this last time. I have this model. And I was talking about learning the parameters for this. Now, if you learn it with respect to MLE, that would be either normal Bayes sort of an idea or actually doing EM. If you decide to do Bayesian learning, then there's no learning. Then basically the network looks like this. So you are talking about, how the distribution, there is a prior on the distribution of the categories, which is from which you actually pick the category. And then similarly, there is a prior on the distribution of words with respect to category, from which you pick the distribution. These 2 priors are then themselves guided by underlying Dirichlet priors. This would be a Dirichlet prior of K dimensions because there are K categories. And this would be a Dirichlet prior of V dimensions because there are V words. You see what I'm saying? Now notice that these guys are living outside of the plates. That means they will remain the same for every unrolling of every inside as well as outside plate. Okay, now this is basically the Bayesian learning perspective. In this case, what learning do you do? The thing to realize is, what do you learn here? Nothing. You don't learn anything. Okay? Because in Bayesian learning, you don't learn anything. Okay? But then how are the probabilities set? Well, you sampling these probabilities, this and this, how are they set? You just sampled from the prior. Okay? But then how does the data change anything? data changes the posterior of these probabilities. How do I compute the posterior? I do inference. In the LDA paper, there is no learning step. Actually, there is one in the sense, these things, they tend to sometimes try to get it by MLE estimate. But if you're doing Bayesian learning, then essentially the rest of it is just inference. And when you are doing the inference, you can use any inference method. And that's why they use collapse gift sampling, which is a particular kind of gift sampling. It's very important to understand this at this level because this is what is repeated in the next level, which is LDA. Okay. I'll just state this now, that from single topic model to multi-topic model, which is what we are about to do, which will become LDA. But then now LDA is no longer a stranger in town. It's just a logical continuation of everything we have discussed. It's just a small extension. Okay. So unigram model assumes all documents are drawn from the same word distribution. The single topic model assumes that the word distributions are topic dependent, which is a good thing. This is what LDA does too. But that every document has only exactly one topic. This could be a bad thing because sometimes a document can have multiple topics. And that's a more general case. And it's some sort of mixture of topics. Right? Now, so what I want to do is I want to keep this but change this. So how about I still consider topics to be distributions over words, but I consider documents to be general distributions over topics, not degenerate distributions over topics. Previously, we are looking at degenerate distributions where you will have one for one topic and zeros for everybody else. Now I'm just saying it can be any normal distribution over k topics. If you do this, then you essentially are considering documents really as, you know, first-class objects in the k-dimensional simplex. Okay? So now I kind of like the fact that when you do this, you can think of documents now essentially are, I mean, the simplex aspect, I mean, you should remember belief states. Belief states live on simplexes on the states too. So documents live on the simplexes of topics. Topics live on the simplexes of words. Okay? So that's what the LDA does. And let me just show this to you and we'll come back to the discussion, real discussion next class. So here in a topic like this, in a document like this, the picture that LDA guy has in mind is that before I showed you a document, I know previously I had to tell you which topic the document is from. Now I have to tell you, you know, among the k topics, this document has 70% topic 1, 10% topic 3, and 10% topic 4, 5% topic 7, and 5% topic 9. That's what I told you. This is my document. Now it turns out once I do that, then all documents of that particular mixture are statistically equivalent. They are like his HHTT versus my HTTT. They may look superficially different, but they're statistically equivalent. Okay, now what do I do then? The model essentially says that for each word in the document, I first pick a topic from which that word is generated. Okay, and so the topic is picked from this distribution. Okay, now the color coding here is there is a yellow topic, a red topic, and a blue topic, etc. And for each word, I basically go to this distribution and pick a topic. So here I got a red topic, then a yellow, then a red, yellow, blue, blue, blue. Okay, and then using that, I will generate the next word, next word, next word. Okay, for each topic, there is a distribution like this, because topics are nothing but distributions, our words. So now I know that I'm going to generate a red word. I will go to the red distribution, pass my v-dimensional coin, and then you tell me what word, I'll pick that word and put that word there. That's LDA. It's very close to single topic. It's more realistic because it's allowing documents to have multiple topics. Right? And the picture, so now notice, of course, that you could say this picture is kind of weird. This picture almost acts as if you are generating the words in the order, but really you know that the order has already gone out the window. All these models think words are bags. Okay, so it's not surprising that according to this, the first word is from topic 1, second word is from topic 2, third word is from topic 4, fourth word is from topic 5. People will have a whiplash reading such a novel, mental whiplash, right? Okay, but that doesn't matter because before we even saw this, we already converted this into a big bag of words. And you are just generating this bag again yourself. So you have a bag, I'm going to just put stuff into this bag. Now we can compare both of our bags. You don't care which order I put things in. The bags have the same number of apples, oranges, you're happy. Right? Okay? So that's basically what the LDA model is. And then, of course, the tricky part, of course, is, so the picture, by the way, and I'll come back to this again, start next time. The picture looks a little more complicated than before. So there is, the unrolled version of the LDA model looks like this. For each word, there is a topic, I pick the topic with respect to the distribution, and then given the topic, then I pick the word. And these words now have the parents, as their parents, both the topic and the distribution for that topic, which is stored in this beta variable. Okay, this is my network. If I have 3 documents, then this is the network I'm trying to work with. This is my story of how these documents, 3 documents with 4 words each are generated. The tricky part, of course, is I'm only given the words. Okay, and these guys are set up front using sampling from the priors. And then you compute the posterior. So you think of this as a huge base network which has pre-specified parameters, and then I tell you all of these words have specific values. So this is the evidence. Given the evidence, I'm just asking you to compute the posterior on theta. That's an inference problem. That's not a learning problem. It just so happens that once you do that, you can essentially generate new documents. Okay, so we'll stop here. Please read the LDA paper and come back, and the next 2 classes will complete.